Good morning to one and all. Myself, Arun Kumar K, Assistant Professor, Department of Aeronautical Engineering in MLR Institute of Technology, Hyderabad. So, in the previous lecture, we discussed about various quasi-static process and its purpose and how to sense that various thermodynamic quasi-static process, and what are the process also we discussed. So, with that actually, we can able to solve the numerical problem in a quasi-static process. See, this is a given problem. So this is we are having a piston cylinder device, right? A piston cylinder device operates 1 kg of fluid at 20 atmospheric pressure, and the initial volume is given as 0.04 meter cubic. And the fluid is allowed to expand reversibly. See, here itself actually we can able to find out what kind of process actually we are going to consider. We know that reversible processes are nothing but actually ideal processes, and irreversible processes are nothing but actual processes. So in the question actually they won't mention any quasi-static process over here. So with the term reversible is nothing but actually we should come to know this process comes under the quasi-static one, right? Yes. See, they have given a piston cylinder arrangement device they have given. So in that actually it operates only 1 kg of a working substance, that is a fluid actually they have given, which is maintained at 20 atmospheric pressure, right? The initial volume is given as 0.04 meter cubic, and the fluid is allowed to expand reversibly. So expansion process is taking place reversibly, right? Following a process. So this process PV power, so this is actually power we are having, PV power, right? PV power 1.45 is equal to constant. So this comes under actually adiabatic process, and reversible adiabatic process is nothing but isentropic process we are having, right? So that the volume becomes double, right? During this reversible expansion process, the volume gets doubled. So the initial volume they have given, initial pressure also they have given. So the volume at the end of the expansion process, it becomes double. Then the fluid is then cooled at constant pressure process, right? Is then cooled at constant pressure until the piston comes back to the original position. So they have given another process also, constant pressure process. The first one is nothing but reversible adiabatic, that is isentropic, right? Or otherwise PV power gamma equal to constant. From that we will come to know, right? So until the piston comes back to the original position, keeping the piston unaltered, right? Heat is added reversibly. See here the heat is added again reversibly. So here also we can able to say this comes under a quasi-static process, right? So here the term the piston unaltered is nothing but actually we supposed to know volume equal to constant. So the first process is nothing but actually we call it as, this is the first process, reversible expansion process or reversible adiabatic or isentropic. Next one is nothing but constant pressure process, when until the piston comes back to the original position, right? And the third one is nothing but actually we call it as piston remains unaltered. So when the piston remains unaltered, we are adding the heat energy, right? So if I am adding the heat energy in the sense, see that is the process, heating process we are taking place, that is in the reversible manner we have taken. So which means the piston unaltered is nothing but volume remains constant, V equal to C. So this is your third process, right? So until it restore it to the initial pressure. So the initial pressure they have given 20 atmospheric pressure, and calculate the work done in the cycle, right? So it comes back to the restore to the initial pressure itself they have given. So which means the combination of more processes is nothing but actually we call it as a cyclic process, right? So the final state of final process, right, comes to the initial state of initial process. Got it? See here we have considered only 3 processes over here. So what does that mean actually? 1 to 2 first process, and 2 to 3 next process, right? And the third process 3 to again it goes to 1. This one is nothing but this one. So in individual process I supposed to say 1 to 2, 2 to 3, and 3 to 1. Right? In 1 to 2, 1 is the initial state and 2 is the final state. In 2 to 3, 2 initial, 3 final. And 3 to 1, 3 is nothing but initial and 1 is nothing but final. That is why I said in the final process, the final state, right, merges with the initial process, initial state. Then we can able to say that is nothing but actually the cyclic path. Right? It follows the cyclic path. So we need to calculate the work done for all this process. Right? So work done formulas in the previous lecture we derived for the individual processes. Right? See here, first of all, whenever the problem is given, so it is very better to understand the problem with respect to the PV diagram. So the first step is nothing but always draw the PV diagram for the given problem, numerical problem. Right? So what is that first problem, first process they have given? It is nothing but expansion, reversible expansion, reversible adiabatic. That follows always. What is that formula? PV power gamma equal to C. That is the mathematical formula for the given process. How it follows actually in the curvature manner. Right? Like the quarter hyperbolic curve manner. That is what it follows with respect to the PV power gamma equal to constant. So during the expansion process, everyone knows that the volume get increases as well as the pressure got decreases. That is what happens. Right? And in 2 to 3 process, see, so that the volume gets doubled also. So they have given V1 over here is equal to V3. From the graph we'll come to know, right? Later we'll see. And this is your V2. Right? So they have given during that expansion process the volume get doubled. Doubled in the sense 2 times of V1. So what is the V1 actually they have given? 0.04. So 0.04 will give you 0.08 meter cubic. Right? If it is specific volume. Why? Because the mass is specified over there 1 kg. So meter cubic per kg also we can able to mention. That is what they have given. Right? And what is the 2 to 3 process? It is constant pressure process. Right? It is constant pressure process until it reaches the initial volume, they said. Right? We need to cool down the system, right? Until it reaches the volume V1, we are maintaining the pressure as constant. So that is your 2 to 3 process. Right? So in that, if I maintain the pressure as constant actually, right, the volume has to decreases to cool down. Next one, the piston remains unaltered. Right? We are adding the reversible heat addition process. So this is your P equal to C. P equal to C. And the piston remains unaltered. So the piston remains unaltered in the sense, always that is nothing but actually we call it as V equal to V1 equal to V3. Right? And heat is added reversibly so that it reaches the initial pressure. So we know that during heat addition process, the pressure get increases. Right? So until that actually the piston remains unaltered. Got it? Right? So during expansion process, the piston get moves from, we can't able to consider this as engine actually. So this is moves with respect to that. The hot gases pushes the piston downward so that it expanded. Right? It expanded in this way. This is your point 1 and this is your point 2 we are having. Right? Point 1 actually in the mathematically we will consider this is around 1. Why? Because it is double, right? So here we will consider this as 1. Right? This as 1. Again 2 to 3. Right? With respect to the 2 to 3. 2 to 3 again it reaches the over here. There the cool down process takes place with respect to the constant pressure process. The pressure with respect to the gases remains constant. And again they are adding the heat energy over here when the piston remains unaltered over here. So that is what this V1. Again V1 is nothing, the point is nothing but 3. Right? So like that cycle keep on goes. again the heat is added, again get expanded. Again, with respect to the constant pressure process, I am ejecting the heat energy. Again, we are heating the hot gases or the working substance, whatever it may be. So this process repeats. These are the cyclic process we are having, right? So with respect to that, see how much overall total work done is nothing but. So total work done is nothing but we are having work done equal to, right, work done of 1 to 2 process and work done of 2 to 3 process and work done of 3 to 1 process. We know that for the 1 to 2 is nothing but it obeys PV power gamma equal to constant, right, and 2 to 3 is nothing but it obeys with respect to the which one, pressure equal to constant, and W equal to 3 to 1 is nothing but constant volume. So for constant volume, the work done equal to 0. For constant pressure process, what is the formula we are having? P of V2 minus V1. Here which is the final state? V3. So V3 minus V2. Right? And what about this one? PV power gamma equal to constant. We need to substitute that in the formula W equal to integral P dV. Right? In that P actually we supposed to substitute V power gamma. And solve that on your own, you'll get P1 V1 minus P2 V2 by gamma minus 1. Actually, we'll get see P power V power minus gamma over here. Instead of P, I can able to substitute V power minus gamma into C. V power minus gamma is nothing but if I integrate V power minus gamma plus 1 by minus gamma plus 1. Right? So I'll write over here. See here for which one? For isentropic process integration, instead of P I can able to substitute C by V power gamma. What is that V power gamma we are having? V power gamma is nothing but V power minus gamma into C into dV. Right? So I can take C as a common constant parameter outside. So V power minus gamma, this is gamma, into dV. So if I do the integration, what will you get? So V power C into V power minus gamma plus 1 by minus gamma plus 1 of V2 and V1. Right? So I can able to get with respect to this V2 power minus gamma plus 1, right, V2 power minus gamma plus 1 minus V1 power minus gamma plus 1 by constant parameter minus gamma plus 1. Right? Always gamma is nothing but greater than 1. So gamma of air, we are having 1.399 or 1.4. Gamma of hot gas, that is also we will consider as 1.33 or 1.4. So in that range actually we are having. So always gamma is nothing but greater than 1. So that is why the denominator term we are changing with respect to in the positive way. Right? So I can't able to keep this as this. I can able to write 1 minus gamma. Is that right? 1 minus gamma is nothing but always I'll get the negative. That is I am taking this minus over here and in the denominator also and as well as in the numerator I am taking minus comma. So that I can able to substitute, I can able to get this values P1 V1 minus P2 V2 by gamma minus 1. So there actually C I am having, right? So the C is nothing but we are having P1 V1 power gamma is nothing but C, and P2 V2 power gamma is also C. So with respect to 2 parameter, I can able to substitute this C in terms of P2 V2 power gamma. Right? So C is nothing but actually I can able to write P1 V1 power gamma which is equal to P2 V2 power gamma. So that see these two terms I can able to take any one. So for our simplification purpose with respect to C into V2 for this term, this C actually I am going to consider P2 V2 power gamma. That is why V2 power gamma and V2 power minus gamma get cancelled, we are getting V2. So we will get P2 V2. Here also C into V1, right? C into V1. So what is that C into V1 in the sense? C is nothing but here actually I am getting P1 V1 power gamma. So there also V1 power gamma and V1 power minus gamma get cancelled. So we get P1 V1. So I will take the minus over here so that it get reversed to P1 V1 minus P2 V2 by gamma minus 1. Right? So in that way actually I is supposed to substitute the formula. So that what is the P1 actually we are having total atmospheric pressure we are having. And what about the V1 actually we are having 0.04 meter cubic we are having. Right? And what about P2 we are having? P2 we need to find out. Right? and V2 we are having as 0.08 we are having. So all these thermodynamic property if you are calculating, I can able to get the value of total work done. So these values you need to calculate on your own. So the first process, whatever we discussed, step 2 process involved in the cycle. First process, that is what isentropic expansion, I said reversible adiabatic, right? And next one is pressure is constant, that is V by T equal to C. Using this relation actually we can able to get, right? And next one is nothing but P by T equal to constant. Got it? So with respect to this, actually I can able to get the value of P2 also. See P2, how to get the P2 value? We know that P1 V1 power 1.45 equal to P2 V2 power 1.45. We know the P1 value, we know the V1 value, we know the V2 value, and P2 we need to calculate. That's it. Right? If I know the P2 value in the previous slide, I can able to substitute this P2 over here, V2 and P1 V1 we know, so that I can able to solve the problem. Right? So P2 equal to P3 over here in the W of 2 to 3. So P2 equal to P3, that is what? Either you can substitute P2 over here. What about V3 and V2? V3 is nothing but we are having as 0.04. V1 is nothing but V2 is nothing but 0.08. So we'll get the work done, right? In terms of negative, we'll get, so that I can able to get the problem. That's it. So like that, actually we need to solve the problem. See, whenever if you want to know the relation between pressure, volume, or pressure and temperature, or volume and temperature, right? So for example, for the macroscopic property, we are having PVT. These are very important with respect to the ideal gas equation, PV equal to MRT, right? If you want to know this coordinates, we supposed to have the relations with respect to the ideal gas equations, right? So with that, actually I can able to get the other values. For example, constant pressure process we said. For example, 2 to 3 process. So V by T equal to constant. So what is that actually? V2 by T2 equal to V3 by T3. Why? Because pressure is constant in the sense we are not having any relation between the pressure. It remains constant. So we are having only the relation between volume and temperature. Right? With that, actually we can able to, with the given data, we can able to find out the other values. Say for example, P by T equal to constant in the sense for constant volume. For constant volume in the sense we are having only relation between which one? Pressure and temperature. So P3 by T3 equal to, what is that? P1 by T1. That's it. So we are having P and T relation for the constant volume process. We are having V and T relation for the constant pressure process. But for isentropic process, we are having PVT relations. So we are having PV, we are having PT, and we are having VT. So 3 possible cases we are having. How to find out that? Actually, with this 2 equation, PV power gamma equal to constant. With the relation, we are having P and B. And another one is nothing but actually we are having PV equal to MRT. Right? So what is it? MRT is nothing but actually we are having C into T for the closed system. PV equal to C into T. Right? Or I can able to write PV by T equal to C. So this is assume this is equation 1 and this is equation 2. With these 2 equations, I can able to get the 3 possible cases. If I divide this 1 by 2 equation, what will happen? PP get cancelled. I am having volume and temperature relation. Already with respect to this isentropic equation, I am having P and T relation, right? Sorry, P and V relation. With this, I can able to get V and T relation. And what is the third possible case? P and T relation. How to get the P and T relation? Either you substitute any one value over there, I'll get the P and T. Instead of V, you just substitute in terms of T over here. I'll get the P and T relation. Right? So with that, actually, I can able to get the relations between the various thermodynamic properties. Okay. So like this, we need to solve the problem for the various ideal processes, or we can say various quasi-static processes. Right. So we need to calculate whatever we discussed, work done for the individual processes. Right. For example, work done for isentropic process and work done for isobaric process and work done for isoporic process. After calculating W for individual process, calculate W for the cycle by summing all. Right. So this is the way of solving the problem. So thank you very much. We'll discuss in the next lecture.